Welcome to the Late Lab. It's lovely to have you here. Before we begin, it would be wonderful to know where in the world you're listening from tonight. Perhaps from a calm bedroom as the day winds down, a quiet corner of the house with the lights softened, a late journey home while the world drifts slowly past the window, or a comfortable chair somewhere far away where the morning has only just begun. Wherever this finds you, hopefully you are warm, safe, and able to settle in for a slow and gentle wander through one of the strangest ideas in modern science. If you enjoy these calm explorations through physics and the universe, please consider liking the video and subscribing to the channel. It genuinely helps this sleepy little corner of science continue drifting along. And to those who are already subscribed, thank you. Truly. Your support means far more than you might realize. Now, the topic tonight is something everyone experiences constantly, yet almost nobody fully understands. Time. It feels steady, dependable, and almost too familiar to question. Seconds tick past, minutes gather into hours, and the quiet rhythm of days slowly turns into years. Life unfolds in a gentle sequence where the past slips behind us and the future quietly approaches. At least, that is how it appears. Because when physicists began looking closely at the nature of time, something deeply surprising emerged. Time does not behave the way human intuition expects. Clocks moving at high speeds tick more slowly than clocks at rest. Time runs slightly faster on mountaintops than it does at sea level, near a black hole, and time can stretch so dramatically that hours for one observer could correspond to years for another. And in some of the deepest modern theories of physics, time may not actually flow at all. Instead, the universe might be structured more like a vast landscape of events, where past, present, and future all exist together within the geometry of space-time. The sense that time is moving forward could be something the human mind constructs as it experiences change. It sounds strange, almost unsettling. But this possibility is not science fiction. It emerges from real physics developed by scientists such as Albert Einstein, Ludwig Boltzmann, Carlo Rovelli, and Julian Barber, each exploring different pieces of the puzzle. The deeper science looks, the less certain it becomes that time is the steady river it appears to be. Instead, as time may be something far more subtle, something that bends with gravity, stretches with motion, and possibly emerges from deeper laws that the universe is only beginning to reveal. So tonight, as the world grows quiet and the rhythm of the day begins to slow, it is worth asking a simple question that turns out to be anything but simple. What exactly is time? And perhaps more intriguingly, what if time itself is an illusion? Time is one of those things that feels so familiar that it rarely attracts much suspicion. It seems obvious. Moments arrive, linger briefly, and then quietly slip away into memory. Morning becomes afternoon. Afternoon softens into evening, and the quiet rhythm of days slowly gathers into months and years. Life unfolds in what appears to be a steady sequence, where the past rests behind us and the future stretches somewhere ahead. From the earliest years of childhood, this pattern becomes deeply ingrained. People learn to wait for birthdays, anticipate holidays, and remember events that have already happened. The mind naturally arranges experiences into a timeline. Yesterday feels fixed, tomorrow feels uncertain, the present moment feels like a moving point that quietly travels forward through life. And yet, that sense of movement raises a subtle question that rarely receives much attention. Is time actually flowing? Or does it only feel that way? To begin exploring that question, it helps to look at how the human brain experiences time in the first place. The curious discovery made by neuroscientists is that the brain does not contain a single clock that measures seconds like a watch or a stopwatch. Instead, the brain appears to assemble the experience of time from several different processes working together. David Eagleman, a neuroscientist known for studying perception and consciousness, has explored how the brain constructs the sensation of duration. His research suggests that the mind does not measure time directly. Instead, it tracks changes in the environment and compares them with stored memories. From this continuous comparison, the brain produces the feeling that time has passed. In other words, the brain is not measuring time itself, it is measuring change. That difference may seem small, but it carries important consequences for how time is experienced. Most people have noticed that time does not always feel consistent. During moments of deep engagement, such as becoming absorbed in a story or concentrating on an interesting task, hours can slip past almost unnoticed. Yet during moments of boredom or discomfort, even a few minutes can feel surprisingly long. The clock on the wall may insist that exactly the same amount of time has passed. But the experience tells a very different story. This strange elasticity of time perception reveals that the brain's internal experience of time is flexible rather than rigid. Attention, emotion, and novelty all influence how long an event appears to last. Moments filled with rich sensory information often seem longer in hindsight because the brain stored more details during that experience. Routine, on the other hand, tends to pass more quietly through memory. Something similar happens during moments of sudden danger. People involved in accidents often report that events seem to unfold in slow motion. A falling object appears to descend more slowly than expected. A brief instant seems to stretch into something far longer. Researchers studying these reports believe the brain temporarily increases the rate at which it processes information during stressful situations. More sensory details are captured, creating the impression that time itself has slowed. Yet outside, observers see no change in the clock, only perception shifts. The brain is quietly adjusting how experience is recorded and interpreted. This observation leads to an intriguing conclusion. The human sense of time passing is not simply a direct reading of the universe. It is partly shaped by the way the brain processes events, stores memories, and directs attention. But perception is only one part of the story. Deep within the body, another system is also keeping track of time in its own way. This system operates through biological rhythms known as circadian rhythms. The word circadian comes from Latin roots meaning about a day. These rhythms follow roughly a 24-hour cycle and influence sleep, hormone release, metabolism, and many other biological processes. One of the scientists who helped pioneer the study of these rhythms was Franz Hallberg, a researcher often regarded as one of the founders of chronobiology. Chronobiology is the scientific study of biological timing systems. Hallberg's work revealed that living organisms possess internal clocks that continue functioning even in the absence of external cues such as sunlight. In carefully controlled laboratory environments where light cycles were removed, many biological processes continued following approximately 24-hour rhythms. This suggested that the body carries its own internal timekeeping system. Later research helped uncover the mechanisms behind these rhythms. Scientists such as Joseph Takahashi identified specific genes that regulate biological clocks within cells. These genes participate in feedback loops that switch certain proteins on and off across a daily cycle, creating rhythmic patterns throughout the body. Inside the brain, a small region called the suprachiasmatic nucleus acts as the central coordinator of these rhythms, and this structure contains only around 20,000 neurons, yet it synchronizes biological timing throughout the entire body. Light entering the eyes sends signals to this region, gently adjusting the internal clock each day so that it remains aligned with the rotation of the Earth. Without that daily adjustment, the body's internal rhythms would slowly drift away from the natural day-night cycle. So in a very real sense, human beings carry an internal sense of time within their own biology. Yet even this biological clock is not measuring seconds the way a mechanical clock does. Instead, it tracks cycles, patterns, and repeating processes that occur across roughly 24 hours. The distinction matters. Mechanical clocks measure intervals between events. Biological clocks regulate cycles of activity. But neither system necessarily reveals what time actually is. They only track change. The Earth rotates once every 24 hours. The planet travels around the Sun once every year. Hearts beat, cells divide, and neurons fire in intricate patterns. The world is full of processes unfolding moment by moment. From these countless changes, the mind constructs a continuous story. A story called time. For most of human history, that explanation seemed perfectly sufficient. Time was simply the measure of change in the world around us. Clocks, calendars, and astronomy allowed societies to track that change with increasing precision. Yet, as science advanced, particularly during the past few centuries, something surprising began to emerge. The deeper scientists examined the laws governing the universe, the less certain it became that time behaves the way human intuition suggests. The flow of time that feels so natural in everyday life may not reflect the deeper structure of reality at all. Instead, the universe may operate according to principles where time behaves very differently from the steady stream people experience. And that possibility leads directly toward one of the most intriguing scientific questions ever asked. Is the flow of time a fundamental feature of the universe, or could it be something that only appears to exist from the perspective of human experience? Long before clocks ticked on walls or wristwatches quietly counted seconds, human beings were already trying to understand the nature of time. The experience of change was impossible to ignore. Day turned into night. The seasons moved in repeating cycles. Years and generations rose and fell across the landscape of history. People could see that events unfolded in a sequence, yet explaining what that sequence actually meant proved far more difficult. Early thinkers did not approach time through laboratory experiments or mathematical equations. Instead, they approached it through philosophy, observation of the natural world, and careful reflection about the nature of existence itself. These early ideas were often shaped by the rhythms of the sky, the cycles of agriculture, and the deep human awareness that life unfolds between birth and death. One of the most influential early thinkers to explore the nature of time was the Greek philosopher Aristotle, who lived in the 4th century before the Common Era. Aristotle proposed a remarkably simple but powerful idea. He argued that time is closely connected to change. In his writings, particularly in a work known as Physics, Aristotle described time as the measure of motion, with respect to before and after. In other words, time was not something separate from events in the world. It was the way human beings counted change as it occurred. This view placed time firmly within the unfolding of the universe rather than outside it. If nothing changed, Aristotle suggested, time would have no meaning. A universe completely frozen in place would contain no motion, no transformation, and therefore no measurable passage of time. Change, in this philosophical framework, was what made time visible. The idea may sound abstract, but it was rooted in everyday observation. Shadows move across the ground as the sun travels across the sky. Seeds grow into plants. Rivers carve their paths through landscapes. Every natural process unfolds gradually, and the mind interprets these unfolding processes as time passing. Yet not everyone agreed that time could be understood so easily. Several centuries later, a very different perspective emerged in the writings of Augustine of Hippo, a philosopher and theologian who lived during the 4th and 5th centuries of the Common Era. Augustine spent considerable effort thinking about the nature of time while reflecting on the relationship between human experience and divine eternity. In one of his most famous passages, Augustine posed a deceptively simple question. What was happening before the universe began? At first glance, the question seemed straightforward, but Augustine recognized a subtle problem hidden within it. If time itself began with the creation of the universe, then asking what happened before that moment might not make sense at all. Without time, there would be no earlier or later, no sequence of events, and therefore no meaningful way to speak of before. Augustine concluded that time might exist only within the universe rather than outside it. Eternity, in his view, was not simply an infinite stretch of time extending forever into the past and future. Instead, eternity was something fundamentally different from time altogether. While time unfolds moment by moment, eternity exists all at once. This idea introduced a profound philosophical contrast. Human beings live inside time, moving from past to present to future, while the concept of eternity suggests a reality that exists beyond that sequence entirely. Then, around the same broad historical period, other cultures were developing their own interpretations of time. Many ancient traditions did not see time as a straight line moving endlessly forward. Instead, they saw it as something cyclical. Ancient Hindu philosophy provides one of the most striking examples of this perspective. In several classical texts, including the Puranas and other cosmological writings, the universe is described as unfolding across vast repeating cycles known as yugas. Each cycle includes periods of creation, stability, decline, and renewal. When one cosmic cycle ends, another begins. Rather than imagining a single beginning followed by a single end, this worldview describes reality as a continuous process of cosmic rebirth. Similar ideas appeared in early Greek Stoicism, and philosophers associated with the Stoic tradition proposed that the universe periodically undergoes a process known as ekpyrosis, a cosmic renewal in which the universe dissolves into fire before being reborn once again. The cycle then begins anew, repeating indefinitely. In both cases, time was not understood as a one-way journey from a beginning toward a final conclusion. Instead, time resembled a circle, endlessly repeating the same grand patterns across immense stretches of existence. These philosophical ideas were not merely abstract speculation. They were strongly influenced by careful observations of the sky. Long before telescopes existed, ancient astronomers carefully tracked the motion of celestial bodies. The sun rises and sets each day. The moon moves through a repeating sequence of phases roughly once every 29.5 days. Constellations shift slowly across the sky through the course of the year. These patterns were stable enough that early civilizations began building systems of timekeeping based on them. In ancient Egypt, priests observed the rising of a bright star called Sirius, whose appearance in the dawn sky closely matched the seasonal flooding of the Nile River. This annual cycle helped structure agricultural planning and religious festivals. Similarly, the ancient Babylonians developed detailed astronomical records that tracked the movements of planets and stars across many years. These observations allowed them to construct calendars and predict celestial events with impressive accuracy. These early timekeeping systems did not measure time in seconds or milliseconds. Instead, they measured repeating cycles in nature. Days, months, and years became the natural units through which societies organized their lives. In this sense, early understandings of time were deeply connected to astronomy. The sky itself became the first clock. As civilizations grew more complex, mechanical timekeeping gradually emerged. Water clocks, sundials, and later mechanical clocks allowed societies to divide the day into smaller and smaller intervals. Yet even with these tools, the deeper nature of time remained a philosophical mystery. Was time an independent feature of reality? Or was it simply a way human beings described change? Across ancient philosophy, theology, and early science, three broad ideas began to take shape. Some traditions viewed time as eternal and unchanging, existing independently of the events within it. Others viewed time as cyclical, endlessly repeating across cosmic ages. Still others believed that time might be intimately connected to consciousness itself, existing only as a framework through which minds organize experience. These early ideas did not settle the question. But they did something equally important. They revealed that time, despite feeling completely obvious, might not be simple at all. And that realization quietly set the stage for the scientific revolutions that would arrive centuries later, when physicists began examining time not only as a philosophical idea, but as a measurable feature of the universe itself. By the late 17th century, the understanding of time began to shift in a profound way. Philosophers had debated its nature for centuries, but a new kind of investigation was emerging. Instead of relying purely on reasoning and reflection, natural philosophers began combining mathematics with precise observation. The universe, they believed, might follow clear and predictable rules that could be expressed in mathematical form. Few individuals shaped this transformation more than Isaac Newton. Newton was born in the year 1642 in England, and would go on to produce one of the most influential scientific works ever written, a book called Philosophiae Naturalis Principia Mathematica. Published in the year 1687, this work laid the foundations of classical mechanics, describing how objects move under the influence of forces. Hidden within this remarkable achievement was a powerful idea about time itself. Newton proposed that time exists as a universal and absolute entity. According to his description, time flows evenly and continuously, independent of the events happening within the universe. Whether planets are moving, apples are falling, or nothing at all is occurring, time continues passing at exactly the same rate. Newton called this concept absolute time. In his own words, he described absolute time as something that flows uniformly by its own nature without reference to anything external. This meant that time was not created by events, nor was it influenced by them. It existed as a steady background against which all motion unfolded. Imagine a vast invisible stage upon which the entire universe performs its activity. Planets move, stars shine, objects collide, and living beings experience life. Yet the stage itself remains unchanged. In Newton's view, time was that stage. It was constant, universal, and the same everywhere. This concept proved extremely useful because it allowed Newton to describe motion with remarkable clarity. If time flows at the same rate everywhere, then the motion of objects can be measured consistently. A falling object accelerates according to precise mathematical relationships. Planets orbit the Sun according to predictable patterns governed by gravity. Newton's laws of motion and universal gravitation relied heavily on this stable framework. Within that framework, one could describe how velocity changes over time, how acceleration influences motion, and how gravitational attraction shapes the movement of celestial bodies. The mathematical relationships Newton developed allowed astronomers to predict the paths of planets and comets with impressive accuracy. To give one example, the English astronomer Edmund Halley used Newton's laws to calculate the orbit of a comet that appeared repeatedly in the sky. Halley predicted that the comet would return after roughly 76 years. When it reappeared in the year 1758, the prediction proved correct. This success reinforced confidence in the Newtonian picture of the universe. Time seemed stable and dependable, exactly as Newton had described it. Yet not everyone agreed with Newton's interpretation. One of his most notable critics was the German philosopher and mathematician Gottfried Wilhelm Leibniz. Leibniz was an extraordinary thinker who made major contributions to mathematics, including the development of calculus independently of Newton. Leibniz approached the question of time from a different philosophical perspective. He argued that time does not exist as a separate entity in the universe. Instead, he suggested that time arises from relationships between events. According to Leibniz, if nothing happened in the universe, there would be no time to measure. Without events to compare, the idea of time passing would lose its meaning. This idea became known as relational time. In the relational view, time is not a container in which events occur. Rather, it is a way of describing how events relate to one another. The interval between sunrise and sunset, the time between two heartbeats, or the duration of a planet's orbit are examples of relationships between events. Without those events, there would be nothing to count. This disagreement between Newton and Leibniz became one of the most famous philosophical debates in the history of science. Newton defended the idea that time exists independently of the things happening within the universe. Leibniz argued that time is inseparable from those happenings. The disagreement was not simply a matter of abstract philosophy. It touched on deeper questions about the nature of reality. If Newton was correct, then time exists even in an empty universe. It flows regardless of whether anything changes. If Leibniz was correct, time exists only when events occur, and relationships between those events can be measured. One perspective treats time as fundamental. The other treats time as derived from change. For many years, Newton's view held the upper hand. His equations successfully described planetary motion, falling objects, and the dynamics of countless physical systems. Engineers used Newtonian mechanics to design bridges, ships, and machines. Astronomers relied on it to predict the positions of celestial bodies. Within this framework, time behaved exactly as expected. It flowed uniformly, unaffected by motion, gravity, or location. A clock ticking in London measured the same passage of time as a clock ticking anywhere else on Earth. Even the distant planets were assumed to experience the same universal time. The success of this picture was so great that it shaped scientific thinking for more than 2 centuries. Newton's model became deeply embedded in physics, forming the foundation upon which many later discoveries were built. Yet the philosophical questions raised by Leibniz never completely disappeared. Even during Newton's lifetime, some thinkers wondered whether the idea of absolute time might be more of a convenient assumption than a true feature of the universe. If time cannot be observed directly, how can its independent existence be confirmed? After all, clocks do not measure time itself. They measure motion. The swinging of a pendulum, the vibration of atoms, the rotation of gears, or the oscillation of electronic signals all serve as proxies for measuring duration. These devices track repeating physical processes, and from those processes people infer the passage of time. But that still leaves an intriguing possibility. Perhaps clocks are not measuring time flowing through the universe. Perhaps they are only comparing one kind of change to another. The ticking of a clock compared with the motion of a planet, the oscillation of atoms compared with the rotation of the Earth. From this perspective, time might be something that emerges from relationships between events, rather than something that exists independently. This question quietly lingered in the background of scientific thought for generations, and eventually, new discoveries in physics would reopen the debate in a dramatic way. Because when scientists began examining the universe at deeper levels, particularly through the study of light, motion, and gravity, they discovered something that would challenge the idea of absolute time itself. The stage Newton imagined might not be as rigid as it first appeared. For centuries after Isaac Newton introduced the idea of absolute time, the universe appeared to behave exactly as his theory predicted. Planets followed their orbits with impressive regularity. Falling objects obeyed predictable laws of motion. Astronomers could calculate the future positions of celestial bodies years in advance with remarkable accuracy. Within this framework, time flowed steadily in the background while events unfolded upon it. Yet one particular phenomenon slowly began to challenge this comfortable picture: light. At first glance, light might seem like a simple thing. It allows people to see the world around them. It travels from the sun to the earth, warming the planet and illuminating the sky. But once scientists began trying to measure how fast light travels, they discovered something deeply intriguing. One of the earliest successful attempts to measure the speed of the light was carried out by the Danish astronomer Ole Rømer in the 17th century. Rømer was studying the motion of Jupiter's moons, particularly a moon known as Io. As Io orbited Jupiter, it periodically disappeared into the planet's shadow and then reappeared. These eclipses followed a regular pattern that astronomers could track carefully. But Rømer noticed something unexpected. The timing of these eclipses seemed to shift slightly depending on where the Earth was located in its orbit around the Sun. When Earth was moving closer to Jupiter, the eclipses appeared slightly earlier than predicted. When Earth was moving farther away, they appeared slightly later. The difference was small, but it was consistent. Rømer realized that the explanation might lie in the time it takes light to travel across space. When Earth was farther from Jupiter, the light carrying the image of Io's eclipse had a longer distance to travel before reaching Earth. That extra distance introduced a small delay. By analysing these delays, Römer estimated that light travels at a finite speed rather than instantaneously. Although his estimate was not perfectly precise by modern standards, the idea itself was revolutionary. It revealed that light takes time to move through space. Later experiments refined these measurements with increasing accuracy. One of the most important figures in this effort was the American physicist Albert Michelson. During the late 19th century, Thayer Michelson developed extremely precise optical instruments capable of measuring the speed of light with remarkable accuracy. Using rotating mirrors and carefully calibrated distances, Michelson measured the speed of light to be roughly 300,000 kilometers per second. In more familiar terms, light travels around the circumference of the Earth more than 7 times in a single second. Even across the enormous distances of space, however, light still takes time to arrive. Light from the Moon takes just over 1 second to reach Earth. Light from the Sun takes about 8 minutes. Light from the nearest star beyond the Sun requires more than 4 years to arrive. The universe, it turned out, does not operate instantaneously. Information travels at a finite speed. At first, this discovery did not seem to threaten Newton's concept of time. Scientists assumed that light behaved like other kinds of waves known at the time, such as sound waves. Sound waves travel through air, water waves travel through oceans, and vibrations move through solid materials. By analogy, many physicists believe that light waves must travel through some invisible medium filling space. This hypothetical medium became known as the luminiferous ether. The ether was imagined as a subtle substance that filled the universe, allowing light waves to propagate through it much as sound waves move through air. If the Earth was moving through this ether as it orbited the Sun, then the speed of light measured on Earth should vary slightly depending on the direction of measurement. Light travelling in the same direction as Earth's motion through the ether might move slightly differently than light travelling in the opposite direction. Testing this idea required extremely delicate experiments. In the year 1887, Albert Michelson and Edward Morley conducted one of the most famous experiments in the history of physics at what is now Case Western Reserve University in Ohio. Using an instrument called an interferometer, they attempted to measure tiny differences in the speed of light along different directions. The experiment split a beam of light into 2 paths arranged at right angles. If the Earth were moving through the ether, then the time required for light to travel along each path should differ slightly depending on the direction of motion. Even a difference of a few millionths of a second would have been detectable with their equipment. But the experiment produced an astonishing result. No difference appeared at all. No matter how the apparatus was oriented, the measured speed of light remained the same. The Earth seemed to move through space without producing any detectable motion relative to the ether. The expected changes simply did not appear. This outcome puzzled physicists. If the ether existed, why could no experiment detect motion through it? Several scientists attempted to resolve this mystery through increasingly creative explanations. One of the most important figures in this effort was the Dutch physicist Hendrik Lorentz. Lorentz proposed that objects moving through the ether might actually contract slightly in the direction of motion. This effect, later known as length contraction, would make it impossible to detect motion through the ether using experiments like Michelson and Morley's. Lorentz developed mathematical relationships describing how measurements of space and time might change for objects in motion. These relationships became known as the Lorentz transformations. Around the same time, the French mathematician and physicist Henri Poincaré expanded upon Lorentz's work. Poincaré recognized that the equations describing these transformations possessed a deep symmetry. He also suggested that the laws of physics might look the same for observers moving at constant speeds relative to one another. This idea became known as the principle of relativity. At this stage, however, the full implications of these ideas were not yet clear. Lorentz and Poincaré had developed mathematical tools capable of explaining the puzzling results of the Michelson-Morley experiment, but the deeper meaning behind those tools remained somewhat hidden. Something strange was happening with measurements of space and time. The equations hinted that space and time might not be fixed and absolute after all. Instead, they seemed capable of shifting depending on motion. Yet few physicists were ready to abandon the familiar Newtonian framework. That final step would require a bold conceptual leap, a leap that would soon arrive from a young patent clerk in Switzerland who began asking a deceptively simple question. What if the speed of light is truly the same for everyone, no matter how they move? By the beginning of the 20th century, physics had reached an unusual moment. Newton's description of motion still worked beautifully for most everyday situations, from falling apples to orbiting planets. Yet the strange behaviour of light had introduced a tension that refused to disappear. Experiments kept insisting that the speed of the light was always the same, no matter how fast the observer moved. This stubborn result suggested that something deeper was happening. In the year 1905, a young physicist named Albert Einstein proposed a radical way of understanding the situation. At the time, Einstein was working at a patent office in Bern, Switzerland, reviewing technical designs for electrical devices. In his spare moments, he was also thinking deeply about the nature of space, motion, and light. His breakthrough came from accepting the puzzling experimental evidence rather than trying to explain it away. Einstein proposed that the speed of light is not merely constant in certain circumstances. Instead, the speed of light is the same for every observer moving at a constant speed, regardless of their own motion. No matter how fast someone travels, light always moves away at exactly the same speed. This idea might sound harmless at first, but it carries astonishing consequences. If the speed of light must remain constant for all observers, then something else must adjust to make that possible. Einstein realized that space and time themselves must change depending on motion. In other words, time does not flow at the same rate for everyone. This insight formed the basis of a theory now known as special relativity. The theory begins with two fundamental principles. The first is the principle of relativity, which states that the laws of physics are the same for all observers moving at constant speeds relative to one another. The second principle states that the speed of light in empty space is the same for every observer, regardless of how they are moving. From these two simple ideas, an entirely new understanding of time emerges. One of the clearest ways to visualize this idea is through a thought experiment known as the light clock. Imagine a device consisting of two mirrors facing each other with a pulse of light bouncing between them. Each time the light travels from one mirror to the other and back again, a single tick of the clock occurs. For an observer standing beside the clock, the light simply moves straight up and down between the mirrors. Now imagine that the same clock is placed inside a spacecraft moving rapidly through space. To an observer inside the spacecraft, nothing appears different. The light continues bouncing between the mirrors exactly as before. But to an observer watching the spacecraft from outside, the situation looks very different. Because the spacecraft is moving forward, the light does not travel straight up and down. Instead, it traces a diagonal path as the mirrors move forward while the light is in transit. The path of the light becomes longer. Since the speed of light must remain constant, the only way to accommodate this longer path is for the time between ticks of the clock to increase. The moving clock runs more slowly. This effect is known as time dilation. Time dilation means that clocks moving relative to an observer appear to tick more slowly than clocks at rest. The faster the relative motion, the stronger the effect becomes. At everyday speeds, the difference is far too small to notice, but at speeds approaching the speed of light, the effect becomes dramatic. Astronauts travelling at extremely high speeds would experience time slightly more slowly than people remaining on Earth. In fact, this prediction has been confirmed through many experiments. One particularly clear demonstration involves particles known as muons. Muons are unstable particles produced when cosmic rays strike Earth's atmosphere. They decay very quickly, typically surviving only a tiny fraction of a second before transforming into other particles. Yet when muons move through the atmosphere at speeds close to the speed of light, they survive much longer than expected. From the perspective of observers on Earth, their internal clocks appear to slow down. Particle accelerators have repeatedly confirmed this effect. facilities such as the European Organisation for Nuclear Research, commonly known as CERN, routinely accelerate particles to enormous speeds. Measurements show that rapidly moving particles experience time differently than stationary observers. Time dilation is not merely a theoretical idea, it is a measurable physical phenomenon. Another famous confirmation came from a remarkable experiment conducted in the early 1970s by physicists Joseph Haefel and Richard Keating. They placed extremely precise atomic clocks aboard commercial aircraft and flew them around the world. Some flights travelled eastward, others westward. After the journeys were complete, the airborne clocks were compared with identical clocks that had remained on the ground. The results matched the predictions of relativity. The clocks that travelled at high speeds experienced tiny but measurable differences in elapsed time. Although the changes were extremely small, only a few billionths of a second, the agreement with Einstein's theory was unmistakable. Even modern technologies quietly rely on these relativistic effects. The global positioning system uses satellites orbiting Earth to determine precise locations on the planet's surface. The atomic clocks aboard these satellites tick at slightly different rates compared with clocks on Earth, due to their speed and altitude. Engineers must account for these relativistic effects to maintain accurate navigation. Without corrections based on Einstein's theory, the system would accumulate navigation errors of several kilometers each day. While Einstein provided the conceptual breakthrough that reshaped the understanding of time, other scientists played crucial roles in revealing the deeper structure behind these ideas. One of the most important contributors was the mathematician Emmy Noether. Working in the early 20th century, Noether developed a profound connection between symmetry and conservation laws in physics. Her work showed that whenever a physical system possesses a symmetry, a corresponding conservation law must exist. For example, the symmetry of physical laws with respect to time leads to the conservation of energy. Noether's theorem revealed that time itself is woven deeply into the mathematical structure of physics. The way the laws of nature remain consistent over time is directly linked to one of the most fundamental conservation principles in science. Although Noether's work is sometimes less widely discussed than Einstein's, her insights reshaped theoretical physics in lasting ways. The emerging picture of time was becoming increasingly strange. Time no longer appeared to be a universal background ticking steadily for everyone in the universe. Instead, it depended on motion. Observers moving relative to one another could measure different durations between the same events. Two clocks could disagree. Both could be correct. This idea would have seemed unimaginable within Newton's framework. Yet experiment after experiment confirmed that Einstein's description was closer to reality. Time, it turned out, was not absolute. It was relative. And once the idea of relativity entered physics, something remarkable began to unfold. Einstein had shown that measurements of time depend on motion, and that observers moving at different speeds may disagree about how much time has passed. But the deeper meaning of this discovery was not immediately obvious. It would take a mathematician's perspective to reveal the full picture. That perspective came from Hermann Minkowski. Minkowski had once been one of Einstein's professors in Zurich, and he approached relativity through geometry rather than purely through physical intuition. In the year 1908, Minkowski presented an idea that transformed how scientists understood space and time. Instead of treating them as separate entities, he suggested that they should be understood as parts of a single unified structure. He called this structure spacetime. In everyday experience, space and time appear quite different. Space describes where something is located. Time describes when something happens. The two seem like separate ingredients of reality. Minkowski proposed that this distinction is partly an illusion created by human perception. In the deeper mathematical description of the universe, space and time form a four-dimensional framework. 3 dimensions describe position in space. 1 dimension describes position in time. Together they form a single geometric structure within which every event in the universe occurs. This idea is sometimes summarized in one of Minkowski's most famous statements. space by itself and time by itself are doomed to fade away into mere shadows, and only a union of the two will preserve an independent reality. At first this sounds abstract, but the idea becomes clearer when considering how events are described in physics. Rather than speaking separately about where something is and when it happens, physicists describe an event as a specific point in space-time. An event might be something simple, such as a flash of light occurring at a certain location and moment. To describe that event fully, one must specify 3 spatial coordinates and 1 time coordinate. Together, these 4 values locate the event within the 4-dimensional structure of space-time. Once this perspective is adopted, the motion of objects through the universe becomes something slightly different from what everyday intuition suggests. Instead of objects moving through space while time flows independently, objects trace paths through space-time. These paths are known as world lines. A world line represents the history of an object as it moves through both space and time. For example, imagine a person sitting quietly in a chair for several minutes. In space, their position may remain nearly constant, but in space-time, their world line continues to extend forward because time is progressing. Now imagine someone walking across a room. Their world line curves through space-time as both their spatial position and their time coordinate change. This way of thinking allows physicists to visualize motion in a new way. One particularly useful tool for doing this is called a Minkowski diagram. A Minkowski diagram is a graphical representation that shows how space and time coordinates relate to each other for different observers. In these diagrams, one axis represents time while another represents space. The paths of objects and light can then be plotted within this framework. Straight lines represent objects moving at constant speeds, while the path of light forms a special boundary that cannot be crossed by slower moving objects. These diagrams reveal something fascinating. Observers moving at different speeds slice space-time differently when they define what counts as the present moment. 2 observers in relative motion may disagree about whether 2 events happened simultaneously. What one observer considers happening at the same time, another observer may see as occurring at different times. This effect is known as the relativity of simultaneity. In the Newtonian picture of the universe, everyone shares the same present moment. Time ticks forward uniformly for all observers. But in Minkowski's spacetime, the concept of a universal present disappears. Each observer carries their own version of time depending on their motion through spacetime. Although Minkowski's work provided the geometric language for relativity, it also drew inspiration from earlier developments in mathematics. One of the most influential figures in this broader movement was the German mathematician Felix Klein. Klein developed a program known as the Erlangen program in the late 19th century. This program proposed that different types of geometry can be understood by examining the symmetries that preserve certain structures. In other words, geometry becomes the study of transformations that leave specific relationships unchanged. This idea had a profound influence on mathematical physics. By focusing on symmetry and transformation, its scientists gained powerful tools for understanding the underlying structure of physical laws. Minkowski's formulation of spacetime fits naturally within this geometric tradition. The Lorentz transformations that arise in relativity can be interpreted as geometric transformations within 4-dimensional spacetime. These transformations describe how different observers relate their measurements of space and time to one another. Instead of treating relativity as a set of complicated equations, Minkowski revealed that it could be understood as the geometry of spacetime itself. This shift in perspective had enormous consequences. If space and time form a unified structure, then the passage of time may not be as straightforward as human intuition suggests. The familiar feeling that time flows steadily forward might simply reflect the path that consciousness takes through space-time. In this view, the universe resembles a vast 4-dimensional landscape containing every event that has ever occurred or will ever occur. Past events occupy one region of space-time. future events occupy another. The present moment is not a universal moving boundary sweeping through the cosmos. Instead, it may be a feature of how observers experience their own trajectories through space-time. This idea does not necessarily mean that the future already exists in a predetermined sense. Rather, it highlights how the structure of space-time allows different observers to organize events in different ways depending on their motion. Still, the implication is striking. The universe may not contain a single global clock ticking steadily for everyone. Instead, time may be woven into the geometry of the cosmos itself, inseparable from the spatial dimensions that surround us. What once appeared to be a flowing river of time might instead be a vast and intricate structure through which observers move. And as physicists continued exploring the consequences of this idea, they discovered that space-time itself could bend, stretch, and warp under the influence of gravity. That realization would open an entirely new chapter in the story of time. Once space and time were understood as part of a unified structure, an even deeper question began to emerge. If space-time forms the stage on which the universe unfolds, what determines its shape? Does this four-dimensional structure remain fixed and rigid? Or can it change? Albert Einstein spent nearly a decade exploring that question after developing special relativity. His earlier work had revealed that motion could alter the rate at which time passes, but it did not yet explain how gravity fits into the picture. Newton's description of gravity as an invisible force acting across space had worked well for centuries, yet it no longer felt entirely satisfying within the new framework of space-time. Einstein suspected that gravity might not be a force in the traditional sense at all. Instead, gravity could be a feature of space-time itself. This insight eventually led to the development of a new theory known as general relativity, published in the year 1915. In this theory, massive objects do not simply attract one another through empty space. Rather, they curve the geometry of space-time around them. Objects moving through the curved space-time then follow paths determined by the geometry. A helpful analogy is often used to visualize this idea. Imagine a stretched rubber sheet representing space-time. If a heavy ball is placed on the sheet, the surface bends downward around it. Smaller balls rolling across the sheet naturally move toward the curved region created by the heavier object. The balls are not being pulled by an invisible force. They are simply following the shape of the surface beneath them. In general relativity, massive objects such as stars and planets bend space-time in a similar way. The curvature guides the motion of other objects moving nearby. But something else happens as well. The curvature of space-time does not affect only motion through space. It also affects the passage of time. Einstein's equations revealed that time passes more slowly in stronger gravitational fields. This effect is known as gravitational time dilation. The closer a clock is to a massive object, the more slowly it ticks when compared with a clock located farther away. At first glance, the effect may sound almost magical, but it follows naturally from the geometry of space-time. If space-time bends around mass, both spatial distances and temporal intervals become distorted. A clock near a massive body experiences a different stretch of space-time than a clock located far away. Although this idea once sounded highly theoretical, experiments have confirmed it with remarkable precision. One of the earliest direct tests took place in the year 1959 at Harvard University. Physicists Robert Pound and Glenn Rebka designed an experiment to measure how gravity affects the frequency of light travelling upward in a gravitational field. The experiment was conducted inside a tall tower on the Harvard campus. A beam of gamma radiation was sent from the bottom of the tower to a detector near the top. According to general relativity, light climbing upward in Earth's gravitational field should lose a tiny amount of energy. That energy loss would slightly alter the frequency of the radiation. This effect is known as gravitational redshift. Pound and Rebka measured the shift with extraordinary precision using a technique based on the Mössbauer effect, which allows very small changes in energy to be detected. The results match the predictions of Einstein's theory almost exactly. The experiment demonstrated that gravity influences the behavior of time and energy even over distances as small as a few tens of meters. Later experiments confirmed gravitational time dilation in even more dramatic ways. Atomic clocks, which measure time using the vibration of atoms, are sensitive enough to detect tiny differences in gravitational potential. If one atomic clock is placed on the ground while another is lifted to a higher altitude, the elevated clock ticks slightly faster. The difference is incredibly small, but it is measurable. In fact, modern technology depends on correcting for these relativistic effects. Satellite navigation systems rely on networks of extremely precise clocks orbiting Earth. These satellites move at high speeds and experience weaker gravity than clocks on the ground. As both factors affect the rate at which time passes, organizations such as the European Space Agency and the United States Space Force operate navigation systems that must account for these relativistic differences. Engineers apply corrections based on Einstein's equations to keep the clock synchronized. Without these adjustments, navigation errors would accumulate quickly, and positioning systems used in aircraft, ships, and smartphones would become unreliable. So the strange prediction that gravity changes the rate of time has quietly become part of everyday technology. Yet the consequences of gravitational time dilation become even more dramatic when considering extreme astrophysical environments. Near very dense objects such as neutron stars or black holes, the curvature of spacetime becomes far stronger than anything experienced on Earth. In these regions, time can slow dramatically relative to distant observers. This possibility was explored in detail through the work of astrophysicists studying the life cycles of stars. One of the most influential figures in this field was Subrahmanyan Chandrasekhar. In the 1930s, Chandrasekhar investigated what happens when massive stars exhaust the nuclear fuel that supports them against gravity. His calculations show that stars above a certain mass cannot remain stable after their fuel is depleted. Instead, gravity overwhelms the internal pressure holding the star up, leading to gravitational collapse. This critical limit, now known as the Chandrasekhar limit, helped scientists understand how white dwarf stars form and why some stars eventually collapse into neutron stars or black holes. Although Chandrasekhar's work focused primarily on stellar structure, it also illuminated the extreme conditions where general relativity becomes essential. In regions where gravity becomes extraordinarily strong, the distortion of space-time grows increasingly severe. Close to a black hole, the difference in time between observers can become enormous. A clock falling toward the event horizon of a black hole appears to slow dramatically when viewed from far away. To the distant observer, the clock seems to approach the horizon more and more slowly, never quite crossing it. Yet for the clock itself, time continues passing normally. This strange difference between perspectives reflects the deeper geometry of space-time. Gravity does not merely influence the motion of objects, it reshapes the flow of time itself. The steady ticking that feels so reliable in everyday life turns out to depend subtly on where a clock is located and how strongly gravity curves the space-time surrounding it. Time, once imagined as a universal backdrop flowing evenly everywhere, has become something far more dynamic. It bends with gravity, it stretches with motion, and in the most extreme environments in the universe, it can behave in ways that challenge the very idea of a shared present moment. For most people, time feels like something that moves in a single, unmistakable direction. Yesterday fades into memory, today unfolds in the present, and tomorrow waits somewhere ahead. Broken cups do not leap back onto tables. Melted ice does not spontaneously reassemble into perfect cubes. A puff of perfume released into a room spreads outward and never gathers neatly back into the bottle. These simple experiences reveal something fundamental about the universe. Time seems to possess a direction. Physicists often call this direction the arrow of time. Yet when the fundamental laws of physics are examined closely, something curious appears. Many of the basic equations describing motion and energy look almost identical whether time moves forward or backward. In principle, If a recording of certain physical processes were played in reverse, the equations themselves would not object. And yet the real world clearly prefers one direction. The explanation for this apparent contradiction emerges from a branch of physics known as thermodynamics. Thermodynamics studies how energy flows through systems and how physical processes evolve over time. One of its central principles is the second law of thermodynamics. This law states that in an isolated system, entropy tends to increase. Entropy is a concept that often receives simplified descriptions, sometimes called disorder or randomness. While these descriptions are not entirely wrong, they can be misleading. A more precise interpretation views entropy as a measure of how many microscopic arrangements correspond to the same large-scale state of a system. To understand this idea, imagine a box containing a gas. The gas molecules move rapidly, bouncing in every direction and colliding with one another. From a large-scale perspective, the gas may appear uniform throughout the box, but at the microscopic level, countless different arrangements of molecules could produce that same uniform appearance. Entropy measures how many of those microscopic arrangements are possible. The Austrian physicist Ludwig Boltzmann played a central role in developing this statistical interpretation during the late 19th century. Boltzmann realized that thermodynamic laws emerge from the behavior of enormous numbers of particles. Instead of tracking every individual molecule, statistical physics describes how probabilities shape the large-scale behavior of systems. Boltzmann showed that systems naturally evolve towards states with greater numbers of possible microscopic arrangements. In other words, systems tend to move toward higher entropy. And this insight explains why certain processes occur so reliably in one direction. When perfume spreads through a room, the molecules move from a relatively ordered state to a vastly larger set of possible arrangements throughout the space. The reverse situation, where molecules spontaneously gather back into a tiny bottle opening, is not impossible in principle. It is simply so unlikely that it effectively never happens. This statistical tendency gives rise to the arrow of time. Entropy increases as systems evolve, and that increase marks the direction from past to future. Yet the explanation raises a deeper question. If entropy naturally increases, why did the universe begin in a state of relatively low entropy to begin with? The early universe appears to have been extraordinarily smooth and uniform, especially when examined through observations of the cosmic microwave background radiation. Measurements from missions such as the European Space Agency's Planck satellite reveal that the temperature variations in the early universe were incredibly small. That smoothness represents a state of surprisingly low gravitational entropy. As the universe expanded and matter gradually clumped together to form stars, galaxies, and clusters, gravitational structures began to emerge. Black holes formed in some regions, and black holes possess extraordinarily high entropy according to calculations developed by physicists such as Jacob Bekenstein and Stephen Hawking. The growth of these structures represents an enormous increase in entropy across cosmic time. This leads to an intriguing puzzle. If entropy increases toward the future, then the early universe must have started in a special state with unusually low entropy. But why should that be the case? Modern cosmologists have explored this mystery in several ways. One influential perspective has been developed by physicist Sean Carroll, who has written extensively about the connection between cosmology and the arrow of time. Carroll argues that the direction of time we experience may ultimately be linked to the universe's initial conditions. In other words, the arrow of time may arise not from the laws of physics themselves, but from the particular way the universe began. According to this view, once the universe started in a low entropy state, the statistical tendency toward higher entropy naturally created the forward flow of time that humans perceive. The future contains more possible microscopic configurations than the past. And so physical processes overwhelmingly move in that direction, but not everyone interprets the situation in quite the same way. Philosopher of physics Hugh Price has explored the possibility that time might possess a deeper symmetry than everyday experience suggests. Price has argued that many explanations of the arrow of time rely heavily on assumptions about the past, while neglecting the possibility that boundary conditions in the future might also play a role. In some speculative interpretations, the distinction between past and future may arise partly from how observers interpret information rather than from a fundamental asymmetry in the laws themselves. Although these ideas remain controversial, they highlight how subtle the question of time's direction truly is. At the microscopic level, many physical processes remain compatible with both forward and backward evolution. Yet at the macroscopic level, the growth of entropy produces a clear and unmistakable direction. This contrast between reversible laws and irreversible experience lies at the heart of the arrow of time. The world of atoms and molecules operates according to symmetrical rules, but the vast numbers involved in real physical systems create overwhelming statistical tendencies. From that statistical imbalance emerges the familiar flow of time. Memories accumulate in one direction. Broken objects remain broken. Heat spreads outward rather than gathering spontaneously into concentrated pockets. The arrow of time quietly guides the unfolding of events across the universe. And yet, even with entropy providing a powerful explanation for this direction, the deeper mystery remains. Why did the universe begin in a state so finely arranged that entropy could rise at all? That question continues to linger at the edge of cosmology, hinting that the story of time may reach all the way back to the earliest moments of the cosmos itself. For much of human history, the universe was imagined as something eternal and unchanging. The stars seemed fixed in the night sky, arranged in patterns that appeared permanent across generations. Even as astronomical knowledge improved, many scientists continue to assume that the cosmos as a whole must remain static. The idea that the universe itself might evolve over time once seemed almost unnecessary. That assumption began to change in the early 20th century through the work of astronomers studying distant galaxies. Observations gradually revealed that the universe was not static at all. Instead, it was expanding. One of the key figures in this discovery was the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California during the 1920s, Hubble studied faint smudges of light that earlier astronomers had called spiral nebulae. At the time, it was not yet clear whether these objects were part of the Milky Way or distant systems of stars far beyond it. Using the powerful Hooker telescope, Hubble identified variable stars known as Cepheid variables inside several of these nebulae. Cepheid variables have a special property discovered by Henrietta Swan-Leavitt earlier in the 20th century. Their brightness varies in a predictable way that reveals their true luminosity. By comparing the intrinsic brightness of these stars with how bright they appear from Earth, astronomers can determine their distance. Hubble's measurements showed that these spiral nebulae were incredibly far away, far beyond the boundaries of the Milky Way. They were not small clouds within our galaxy. They were entire galaxies in their own right. This discovery dramatically expanded humanity's understanding of the universe. Instead of a single galaxy surrounded by empty space, the cosmos appeared to contain countless galaxies scattered across enormous distances. Yet Hubble noticed something even more remarkable. When astronomers examined the light from distant galaxies, they found that the wavelengths of that light were shifted toward the red end of the spectrum. This phenomenon is known as redshift. It occurs when light waves stretch as the source of the light moves away from the observer. By carefully measuring these shifts, Hubble discovered a pattern. The farther away a galaxy appeared to be, the greater its redshift. In other words, distant galaxies seemed to be moving away from us, and the more distant they were, the faster they receded. This relationship became known as Hubble's law. It suggested that the universe itself was expanding, with space stretching between galaxies over time. Although Hubble's observations provided powerful evidence, the idea of an expanding universe had actually been proposed slightly earlier by a Belgian physicist and priest named Georges Lemaître. In the year 1927, Lemaître solved Einstein's equations of general relativity and discovered that they naturally allowed for a universe whose scale changes with time. Lemaître proposed that the cosmos began in a very dense and hot state, and has been expanding ever since. He referred to this early state as a primeval atom, an idea that would later evolve into what is now known as the Big Bang model. At first, Einstein himself resisted the notion that the universe might expand. He had originally modified his equations by introducing a quantity known as the cosmological constant to allow for a static universe. When evidence for expansion accumulated, Einstein reportedly referred to this adjustment as his greatest mistake. Today, the expanding universe is one of the most firmly established ideas in cosmology. Observations from telescopes and satellites have provided an extraordinary wealth of supporting evidence. Among the most important discoveries was the detection of the cosmic microwave background radiation in the year 1965 by Arno Penzias and Robert Wilson. This faint glow of microwave radiation fills the entire sky. It represents the cooled remnant of intense radiation produced when the early universe was still extremely hot and dense. The cosmic microwave background acts like a photograph of the universe when it was only a few 100,000 years old. Modern missions have measured this radiation with extraordinary precision. The Planck satellite, operated by the European Space Agency, produced one of the most detailed maps of the cosmic microwave background ever created. Its observations revealed tiny fluctuations in temperature across the sky, representing small variations in density present in the early universe. These slight differences eventually grew into the galaxies and cosmic structures seen today. By analysing this radiation, scientists can estimate key properties of the universe, including its age. Current measurements suggest that the universe has been expanding for roughly 14 billion years. Cosmic expansion therefore connects time with the large-scale history of the universe itself. In cosmology, scientists often refer to a concept known as cosmological time. Cosmological time measures how long it has been since the early hot phase of the universe began. It provides a kind of universal clock for describing the evolution of cosmic structures. Using this timeline, astronomers can describe the formation of galaxies, the birth of stars, and the gradual emergence of complex structures across billions of years. In the earliest moments, the universe was filled with an extremely hot and dense plasma of particles and radiation. As expansion continued, the temperature gradually cooled. Atoms eventually formed, allowing light to travel freely through space. Much later, gravity gathered matter into stars and galaxies. Each stage unfolded over immense spans of time measured on cosmic scales. The expansion of the universe therefore gives time a very different meaning from everyday experience. Human lifetimes are measured in decades. Civilizations span centuries. But the universe evolves across billions of years. Within that vast timeline, even the entire history of human civilization occupies only a tiny fraction. The expanding universe also reveals that time and space are deeply interconnected. As space stretches, the distances between galaxies grow larger. The light travelling across those expanding distances also stretches, producing the redshift observed by astronomers. This means that when telescopes observe distant galaxies, they are also looking back in time. Light from very distant galaxies began its journey billions of years ago. By the time it reaches Earth, it carries information about the universe as it existed long before the solar system formed. Astronomy therefore functions as a kind of time machine, allowing scientists to study earlier stages of cosmic history. Through these observations, the universe reveals a long narrative stretching from its earliest moments to the present day. Cosmic expansion provides the framework within which that story unfolds. Time, in this sense, is not merely something experienced by observers. It is written into the history of the universe itself. When astronomers realized that the universe is expanding, an obvious question soon followed. If galaxies are moving away from one another today, then earlier in cosmic history they must have been closer together. And if that expansion is traced far enough back in time, everything appears to converge toward an extremely dense and hot state. This idea forms the foundation of modern Big Bang cosmology. The phrase Big Bang can sometimes sound misleading. as if it describes an explosion occurring at a particular location in space. In reality, the expansion involves space itself stretching everywhere at once. Every region of the universe was once compressed into a much denser state than it is today. As cosmologists push their calculations further into the past, the densities and temperatures predicted by the equations of general relativity grew increasingly extreme. Eventually, those equations point toward a moment where density becomes effectively infinite, and the curvature of spacetime becomes undefined. Physicists refer to such a point as a singularity. A singularity represents a boundary in the mathematical description of spacetime. It marks a place where the equations used to describe gravity can no longer provide meaningful answers. Instead of producing finite values, the quantities describing curvature and energy simply diverge. In the 1960s, mathematicians and physicists began exploring whether such singularities are unavoidable in Einstein's theory of gravity. Two of the most influential figures in this effort were Roger Penrose and Stephen Hawking. Penrose initially studied gravitational collapse, investigating what happens when massive stars collapse under their own gravity to form black holes. His work demonstrated that under very general conditions, gravitational collapse inevitably produces a singularity hidden inside the black hole. Stephen Hawking later applied similar mathematical reasoning to the universe as a whole. Working together during the late 1960s and early 1970s, Hawking and Penrose developed a series of results now known as the singularity theorems. These theorems showed that if the universe obeys certain reasonable physical conditions and is expanding today, then the equations of general relativity imply that the universe must have begun from a singular state in the past. In simple terms, the mathematics suggested that the Big Bang might represent the beginning of space-time itself. If this interpretation is correct, then asking what happened before the Big Bang may be similar to asking what lies north of the North Pole. The question itself might not make physical sense because time, as described by general relativity, emerges only after that boundary. This idea can feel deeply counterintuitive. Human intuition is built around the expectation that every event has a prior cause, and that time stretches indefinitely into the past. The notion that time itself could have a beginning challenges that expectation. Yet general relativity allows precisely such a possibility. If space-time originates at the Big Bang, then time may not extend beyond that point at all. Stephen Hawking explored this idea further in collaboration with physicist James Hartley. Their work introduced a proposal known as the Hartle-Hawking no-boundary model. In this framework, the earlier state of the universe does not resemble a conventional beginning in time. Instead, time gradually transitions into a structure more similar to space near the origin of the cosmos. In this picture, the universe might be finite yet without a sharp temporal boundary. However, not all physicists agree that the Big Bang necessarily marks the absolute beginning of time. One reason for this uncertainty is that general relativity itself is known to be incomplete when describing extremely small scales and high energies. Near the earliest moments of the universe, quantum effects become important, and the classical equations of gravity may no longer provide an accurate description. For this reason, many cosmologists explore alternative models that attempt to describe what might have occurred before or instead of a singular beginning. One class of ideas involves bouncing cosmologies. In a bouncing universe model, the cosmos undergoes cycles of contraction followed by expansion. Instead of beginning from a singular point, the universe might have previously existed in a contracting phase. As densities increased, new physical processes could have halted the collapse and triggered a transition into expansion. The universe observed today would therefore represent one phase in a much longer cosmic history. Several theoretical frameworks attempt to describe how such a bounce might occur. Some proposals arise from quantum gravity research, where modifications to the equations of general relativity prevent space-time from collapsing to infinite density. Other models explore how exotic forms of energy or modifications to gravity might allow the universe to reverse its contraction before reaching a singularity. Another intriguing possibility appears in cyclic cosmology. Physicists Paul Steinhardt and Neil Turok developed a model in which the universe experiences repeated cycles of expansion and contraction over extremely long timescales. In their proposal, inspired partly by ideas from string theory, the universe exists within a higher dimensional framework where large-scale cosmic events occur periodically. Each cycle begins with a hot and dense phase similar to the Big Bang. After expanding for billions of years, the universe gradually evolves until new processes eventually trigger another cycle. In this view, cosmic history stretches indefinitely both into the past and the future. Time would not have a single origin. Instead, it would extend through an ongoing sequence of cosmic epochs. Other speculative ideas push even further. Some models propose that our observable universe might have emerged from a quantum fluctuation in a larger multiverse. Others suggest that spacetime itself could be an emergent property arising from deeper quantum structures. These possibilities remain highly theoretical, but they illustrate how modern cosmology continues to explore the deepest boundaries of time. Despite these uncertainties, observational evidence still strongly supports the idea that the universe passed through an extremely hot and dense phase early in its history. Measurements of the cosmic microwave background, the distribution of galaxies, and the abundance of light elements such as hydrogen and helium all align remarkably well with predictions from Big Bang cosmology. The open question concerns what happened at the earliest possible moments. Did time truly begin at the Big Bang, or does that moment represent only the earliest point accessible to current theories? At present, science does not yet have a definitive answer. General relativity points toward a beginning. Yes, but quantum gravity may ultimately reshape that conclusion. The boundary between these theories remains one of the most active areas of research in modern physics. What is clear, however, is that the concept of time becomes increasingly subtle as one approaches the origin of the cosmos. Near the earliest moments of the universe, familiar intuitions begin to break down. The distinction between space and time may blur. Quantum fluctuations may dominate the behavior of space-time itself. Even the concept of causality might require careful reinterpretation. In that sense, the question of whether time began with the Big Bang touches the deepest foundations of physics. It asks whether time is a fundamental ingredient of reality or a feature that emerged along with the universe we observe. And for now, the universe keeps that answer quietly hidden within its earliest moments. As the 20th century unfolded, physicists began discovering that the universe behaves very differently at extremely small scales. The elegant geometry of space-time described by Einstein works beautifully for planets, stars, and galaxies. Yet the microscopic world of atoms and particles reveals a new layer of reality governed by quantum mechanics. Quantum mechanics describes how particles behave when their sizes approach the scale of atoms and subatomic structures. At these scales, matter no longer behaves like tiny billiard balls moving through predictable paths. Instead, particles exhibit wave-like properties, probability distributions, and interactions that can appear deeply counterintuitive. Within this quantum framework, time plays a somewhat unusual role. In classical physics, space and time are treated in similar ways. Coordinates describe where something is located and when it occurs, and these coordinates often appear symmetrically in equations describing motion. In quantum mechanics, however, time enters the mathematics differently from spatial variables. The central equation governing many quantum systems was developed by the Austrian physicist Erwin Schrödinger in the year 1926. The Schrödinger equation describes how the quantum state of a system evolves. In its standard formulation, spatial coordinates appear as operators that act on a mathematical object known as the wave function. Time, by contrast, appears as an external parameter that tells the wave function how to evolve. In other words, the Schrödinger equation treats time more like a background clock than a dynamic variable. Space can fluctuate and interact with physical systems within the theory, but time itself simply flows along as a parameter guiding change. This asymmetry raises intriguing questions. If quantum mechanics describes the most fundamental behavior of matter, why does time appear as something external rather than something emerging from the theory itself? Physicists have debated this issue for decades, and the discussion connects deeply with the interpretation of quantum mechanics. One of the earliest and most influential interpretations is known as the Copenhagen interpretation. This perspective was largely shaped by physicists such as Niels Bohr and Werner Heisenberg during the 1920s. In the Copenhagen interpretation, the wave function represents probabilities describing potential measurement outcomes. When a measurement occurs, the wave function appears to collapse into a specific result. Before measurement, a quantum system exists in a superposition of possible states. After measurement, one of those possibilities becomes reality. Within this framework, time enters the theory through the evolution of the wave function between measurements. The Schrödinger equation describes how probabilities change over time, while the act of measurement introduces a sudden update to the system's description. Although this interpretation proved extremely successful in predicting experimental outcomes, it leaves deeper philosophical questions unresolved. What exactly counts as a measurement? Why should observation play such a fundamental role? And perhaps most intriguingly, how does time fit into a theory where physical states appear to change discontinuously during measurement? These questions have inspired many alternative interpretations of quantum mechanics. Among the more unconventional voices exploring the nature of time is the British physicist Julian Barbour. Barbour has argued that time might not exist as a fundamental component of reality at all. Instead, what humans perceive as the passage of time may arise from relationships among configurations of the universe. In Barbour's view, the universe consists of a vast collection of possible configurations, each representing a complete arrangement of matter. He refers to this collection as Platonia, borrowing inspiration from philosophical ideas associated with Plato. Within this framework, what humans experience as time is simply the perception of moving through a sequence of these configurations. Each configuration contains records of other configurations embedded within its structure. For example, memories stored in brains, photographs, geological layers, and astronomical observations all encode information about earlier states of the universe. These embedded records create the impression of a flowing timeline even if time itself does not exist as a fundamental dimension. Barbour's proposal remains controversial, but it highlights how quantum mechanics opens the door to radically different ways of thinking about time. Meanwhile, experimental research continues to explore how quantum systems behave across extremely small timescales. Institutions such as the Max Planck Institute for Quantum Optics in Germany conduct experiments probing the temporal structure of quantum processes. Researchers there investigate how atoms interact with light, how quantum states evolve over incredibly short intervals, and how entangled particles behave when separated across large distances. Some experiments examine events occurring on timescales measured in attoseconds, which represent intervals so brief that billions of them pass within a single second. At such scales, the familiar notion of time as a smooth and continuous flow becomes less obvious. Quantum processes unfold through discrete interactions, energy exchanges, and probability amplitudes. Even more surprising behavior emerges when considering a phenomenon known as quantum entanglement. Quantum entanglement occurs when two or more particles become linked in such a way that their properties remain correlated regardless of the distance between them. Once entangled, measuring one particle immediately determines the state of the other. Albert Einstein famously referred to this phenomenon as spooky action at a distance. Although entanglement does not allow information to travel faster than light, it challenges classical ideas about separateness and temporal order. Imagine two entangled particles created together and then sent to distant locations. Measurements performed on each particle produce correlated results, even when the events occur far apart. Experiments carried out over the past several decades have confirmed these correlations with extraordinary precision. What makes this situation intriguing for the concept of time is that the order of measurements can sometimes appear ambiguous depending on the observer's frame of reference. In relativistic physics, observers moving relative to one another may disagree about which event occurred first. Yet entangled correlations persist regardless of that ordering. This suggests that the underlying quantum relationships may not depend strictly on a single universal timeline. Some physicists have explored whether entanglement might even play a role in the structure of spacetime itself. Research programs investigating quantum gravity propose that spacetime geometry could emerge from networks of quantum entanglement connecting microscopic degrees of freedom. Although these ideas remain highly theoretical, they illustrate how deeply quantum physics challenges traditional assumptions about time. At the smallest scales of reality, time may not behave as a simple background stage on which events unfold. Instead, time might emerge from deeper interactions among quantum states. The classical flow of seconds and minutes could represent a large-scale approximation arising from countless microscopic processes. From this perspective, time may be less like a river steadily flowing forward and more like a pattern emerging from complex relationships. The deeper physicists look into the quantum world, the more the nature of time begins to feel like an open question rather than a settled fact. And somewhere within the strange mathematics of quantum theory, the universe may be quietly hinting that time itself is not quite what it appears to be. As relativity reshaped the scientific understanding of space and time, it also inspired a striking philosophical possibility. If space-time forms a four-dimensional structure containing every event in the universe, then perhaps the past, present and future all exist together within that structure. This idea is often called the block universe. In the block universe picture, space-time is imagined as a complete four-dimensional object. Every event that has ever occurred, every event happening now, and every event that will occur in the future occupies a specific location within that structure. The entire history of the universe exists as a kind of vast geometric landscape. Human beings within this framework experience only a narrow slice of that structure at any given moment. Conscious awareness moves along a path through space-time, creating the impression that time flows from past to future, yet the underlying structure itself may remain fixed. Nothing within the block universe flows or changes in the way everyday intuition suggests. Instead, events simply exist at different coordinates within space-time. The idea emerges naturally from Einstein's theory of relativity. Because different observers moving relative to one another can disagree about which events occur simultaneously, the notion of a universal present moment becomes difficult to maintain. What one observer considers happening now may appear earlier or later to another observer moving at a different velocity. Relativity therefore weakens the idea that the present moment has any special status across the entire universe. If there is no universal present shared by all observers, then the distinction between past, present and future may depend largely on perspective. This observation encouraged some physicists and philosophers to treat all moments of time as equally real. The technical name for this view is eternalism. According to eternalism, every moment in time exists within the four-dimensional structure of space-time. Yesterday remains part of the universe just as much as today. Tomorrow also exists, though observers have not yet reached those events along their world lines. The universe, in this interpretation, resembles a completed story already written into the geometry of space-time. This perspective contrasts with another philosophical position known as presentism. Presentism holds that only the present moment truly exists. The past is gone, remembered only through traces and records. While the future has not yet come into being, under presentism, reality constantly updates itself as time passes. New events come into existence while older events fade into history. The debate between eternalism and presentism has occupied philosophers for centuries, but relativity gave the discussion a new scientific dimension. If simultaneity depends on the observer's motion, identifying a single universal present becomes extremely difficult. Many philosophers of physics therefore consider eternalism more compatible with the structure described by relativity. The implications of this idea can feel strange at first. Imagine space-time as a vast four-dimensional sculpture containing every moment in the history of the universe. The birth of stars, the formation of planets, the emergence of life, and every individual human experience all occupy fixed locations within this structure. Within that framework, the passage of time becomes something experienced by observers rather than something occurring in the universe itself. The sensation of moving from past to future might arise from the way consciousness processes information along a world line through space-time. This interpretation does not mean that people can freely jump to different moments in time. Each observer follows a specific path through space-time determined by physical laws and initial conditions. Nevertheless, the underlying picture suggests that the universe contains a complete timeline rather than a sequence of events gradually appearing. Some of the most unusual consequences of relativity were explored by the mathematician and logician Kurt Gödel. Gödel is widely known for his incompleteness theorems in mathematical logic, but he also made intriguing contributions to cosmology. In the year 1949, Gödel discovered a solution to Einstein's equations describing a rotating universe. In this model, spacetime contains structures known as closed time-like curves. A closed time-like curve represents a path through spacetime that eventually loops back to its starting point. In principle, an observer following such a path could return to an earlier moment in their own timeline. Although Gödel's rotating universe model does not appear to describe our actual cosmos, it demonstrated something important. The equations of general relativity allow space-time geometries in which the usual distinction between past and future becomes blurred. Certain solutions permit structures where temporal ordering behaves in unusual ways. Gödel himself interpreted this result as evidence that the objective passage of time might not exist in the fundamental description of reality. He argued that if physical theories permit universes in which time loops or behave symmetrically, then the intuitive feeling that time flows must arise from human perception rather than from the laws of physics. Not everyone agrees with that conclusion. Some physicists maintain that additional physical constraints such as quantum effects or energy conditions may prevent such exotic structures from occurring in the real universe. Others view Gödel's solutions as mathematical curiosities rather than physical possibilities. Even so, the example highlights how relativity opened the door to new ways of thinking about time. If space-time truly contains all events within a four-dimensional structure, then the familiar feeling of time passing might resemble the experience of reading through a story. The words already exist on the page from beginning to end. Yet a reader experiences the narrative gradually as their eyes move across the lines. In a similar way, consciousness may traverse a path through space-time, encountering events sequentially even though those events already exist within the broader structure. Of course, such ideas remain deeply philosophical as well as scientific. Physics provides mathematical descriptions of space-time, but interpreting what those descriptions mean about reality often requires philosophical reflection. The block universe concept continues to provoke debate among scientists and philosophers alike. Some find it compelling because it aligns naturally with relativity. Others resist it because it challenges the deeply ingrained human sense that time genuinely flows. Regardless of which interpretation ultimately proves correct, the discussion reveals something profound. The universe described by modern physics may be far stranger than everyday intuition suggests. Time, which once seemed like the most obvious and familiar feature of existence, turns out to be one of the most subtle and mysterious aspects of reality. Although physics provides many clues about the structure of time, the human experience of time unfolds in a very different way. People do not experience time as a set of coordinates within a four-dimensional space-time diagram. Thus, instead, time feels like a steady stream carrying events from the future into the present and then gently into memory. Moments appear to arrive, unfold, and fade. This sensation is so natural that it is rarely questioned. Yet when scientists examine how the brain processes information, the experience of flowing time begins to look less like a property of the universe and more like a construction created by the mind. The brain does not receive reality as a perfectly synchronized stream of events. Signals from the outside world arrive through different sensory pathways, each with its own delays and processing steps. Light entering the eyes must be converted into electrical signals by the retina. Those signals travel through the optic nerve and pass through several regions of the brain responsible for interpreting patterns, colours, and motion. Sounds entering the ears follow different pathways, passing through structures in the brainstem and auditory cortex. Touch, smell, and taste rely on yet other neural routes. Each of these signals requires time to travel and be processed. The brain must somehow combine them into a single coherent experience that feels immediate and unified. Neuroscientists have discovered that the brain accomplishes this through mechanisms that integrate information over short windows of time. Rather than reacting instantly to every incoming signal, the brain collects small bursts of sensory information and assembles them into a continuous perceptual frame. This process helps explain why events that occur within a few tens of milliseconds of each other often appear simultaneous. And one area of research investigating this phenomenon focuses on something known as temporal binding. Temporal binding refers to the brain's tendency to group events that occur close together in time into a single perceptual unit. For example, when watching someone clap their hands, the visual sight of the hands meeting and the sound of the clap reach the brain through different pathways. Despite these delays, the brain merges the signals so the action appears synchronized. Neuroscientist Dean Buonamano has explored these processes extensively. His work examines how neural circuits represent time intervals and sequences of events. Buonamano argues that the brain does not rely on a single internal clock. Instead, time perception emerges from patterns of activity distributed across networks of neurons. In this view, the brain functions less like a stopwatch and more like an orchestra of interacting signals. Different neural circuits respond to stimuli in ways that naturally encode timing information. When groups of neurons fire in particular sequences, they create patterns that represent durations and rhythms. These patterns allow the brain to perceive time intervals, predict upcoming events, and coordinate complex actions such as speech and movement. Because these neural processes are flexible, the brain's experience of time can stretch or compress depending on circumstances. Many people have noticed how time seems to behave differently during different situations. Moments of intense excitement or fear can feel strangely elongated, as if events are unfolding in slow motion. By contrast, long periods of routine activity may seem to pass quickly when remembered afterward. Psychologists refer to these distortions as variations in perceived duration. Research suggests that emotional arousal, attention, and memory formation all influence how time is experienced. When the brain processes a large amount of new or emotionally significant information, it often creates denser memories of that period. Later, when those memories are recalled, the interval appears longer because more events are stored within it. During routine or repetitive activities, fewer distinct memories may be formed. As a result, those periods can seem shorter when reflected upon. Another fascinating aspect of time perception involves how the brain constructs continuity. Conscious awareness does not operate as a perfectly continuous recording of reality. Instead, it resembles a rapidly updating sequence of perceptual frames. Some neuroscientists compare this process to frames in a motion picture. Each frame captures a brief slice of sensory input, and the brain rapidly stitches these frames together to create the illusion of smooth continuity. Although the comparison is not exact, it illustrates how the mind constructs a flowing experience from discrete neural processes. Some researchers have suggested that consciousness integrates information over intervals of roughly tens to hundreds of milliseconds. Within these brief windows, sensory events are gathered and combined into a single perceptual moment. As one window closes and another begins, the brain produces the sensation of time moving forward. In this sense, the flow of time may partly reflect how the brain organizes information. And philosophers and cognitive scientists sometimes refer to this phenomenon as the specious present. The specious present describes the short duration over which conscious experience integrates sensory information into a unified moment. Rather than experiencing an infinitely thin instant, the mind perceives a small slice of time containing recent past, immediate sensations, and expectations about what will happen next. This integration creates the seamless feeling of a moving present. These insights raise an intriguing possibility. The universe described by physics may not contain a flowing present moment at all. Instead, the sensation of time passing could emerge from the way biological brains interpret information. Human consciousness constantly updates its internal model of the world, incorporating new sensory data while preserving traces of earlier events. This ongoing process naturally generates the impression that the present is advancing through time. From this perspective, time's flow might resemble a narrative constructed by the brain. Memories store records of past events. Perception brings in signals from the immediate environment. Expectations and predictions guide anticipation of what might occur next. The mind weaves these elements into a continuous storyline that feels like a journey through time. That narrative structure is extraordinarily useful. It allows organisms to plan actions, learn from experience, and anticipate future outcomes. Without such a framework, survival in a complex world would become extremely difficult. Yet the mechanism that makes life manageable may also shape how reality is perceived. If the brain is responsible for generating the sensation of temporal flow, then the universe itself might be more static than everyday intuition suggests. The present moment may not be sweeping forward through the cosmos. Instead, the feeling of movement through time could arise from the activity of billions of neurons quietly coordinating within the brain. In that case, the flowing river of time experienced every day might be less a property of the universe and more a remarkable feature of human perception. Most experiences of time on Earth occur under relatively gentle conditions. Gravity here is moderate, motion is slow compared with the speed of light, and the passage of seconds feels comfortably uniform. Yes, clocks tick steadily whether they sit on a bedside table, a laboratory bench, or a satellite orbiting far above the atmosphere. Yet the universe contains environments where gravity becomes enormously stronger and space-time bends far more dramatically. In those places, the passage of time itself behaves very differently. Among the most extreme environments known in physics are black holes. These objects form when massive stars collapse under their own gravity, compressing matter into regions so dense that space-time curves intensely around them. The boundary surrounding a black hole is known as the event horizon. The event horizon marks the distance from the black hole where the escape velocity equals the speed of light. Once an object crosses that boundary, no signal can travel outward again. Light itself cannot escape. Although black holes may sound exotic, they are not merely theoretical ideas. Astronomers have gathered extensive evidence for their existence through observations of stars orbiting unseen massive objects, through gravitational wave detections, and through direct imaging of the region surrounding event horizons. One of the most striking confirmations came from the Event Horizon Telescope collaboration. This international network of radio observatories combine telescopes across multiple continents to create an Earth-sized virtual instrument capable of resolving extremely small structures in distant galaxies. In the year 2019, the collaboration released the first image of the shadow of a black hole located in the galaxy Messier 87. Later observations also revealed the shadow of the supermassive black hole at the centre of the Milky Way. These images provided remarkable evidence for the extreme gravitational environments predicted by general relativity. Near such objects, the curvature of spacetime becomes so intense that time itself behaves very differently from how it does on Earth. According to general relativity, gravity slows the passage of time. This phenomenon, known as gravitational time dilation, becomes increasingly pronounced as the gravitational field grows stronger. A clock located close to a massive object ticks more slowly when compared with a clock far away. On Earth, the difference is extremely small. But near a black hole, the effect can become dramatic. Imagine a spacecraft approaching the event horizon of a black hole. Observers watching from a safe distance would see the spacecraft's clock ticking more and more slowly as it moves deeper into the gravitational well. Signals sent from the spacecraft would appear increasingly redshifted, meaning their wavelengths stretch and their frequencies decrease. To the distant observer, the spacecraft seems to slow down as it approaches the event horizon. In fact, the approach appears to take longer and longer, asymptotically stretching toward infinity. The spacecraft never appears to cross the event horizon at all, yet for the astronauts inside the spacecraft, time continues to pass normally. Their onboard clocks tick steadily, and their experience of events proceeds without any obvious slowing. From their perspective, the crossing of the event horizon occurs after a finite amount of time. This difference illustrates how dramatically perspectives can diverge in strongly curved space-time. Time is no longer something universal shared by all observers. Instead, each observer follows their own path through space-time, experiencing time according to the geometry surrounding them. Physicist Kip Thorne has explored these extreme gravitational environments in detail. Thorne's work on black holes, gravitational waves, and space-time geometry helped shape modern understanding of how relativity behaves under intense conditions. He has also played an important role in communicating these ideas to broader audiences through books and collaborations with filmmakers interested in portraying relativistic phenomena accurately. Thorne's research demonstrates how the curvature of space-time affects both motion and the passage of time. Near a black hole, the warping of space-time becomes so strong that even light follows curved trajectories around the object. Photons orbiting close to the event horizon can circle the black hole before escaping, creating distorted rings of light known as photon spheres. For objects moving near these regions, the distortion of time becomes profound. A person orbiting near a rapidly spinning black hole might experience time far more slowly than observers far away. Minutes experienced near the black hole could correspond to hours or even years passing in distant regions of space. Although such situations are extraordinarily difficult to achieve in practice, the mathematics of general relativity allows them. These possibilities highlight how the passage of time is deeply linked to gravity and motion. Here, time is not an independent background ticking uniformly throughout the universe. Instead, it responds to the distribution of mass and energy, bending and stretching along with space-time itself. In extreme environments, the familiar sense of a steady universal clock dissolves completely. The concept becomes even more intriguing when considering the regions just outside an event horizon. Near that boundary, tidal forces can grow extremely strong. The difference in gravitational pull between different parts of an object can stretch it dramatically, a process sometimes described with the colourful nickname spaghettification. Yet even before such forces become destructive, the distortion of time becomes remarkable. Clocks near the horizon tick far more slowly relative to clocks far away. Light escaping from that region loses energy as it climbs out of the gravitational well, shifting toward longer wavelengths. Astronomers observing matter falling toward a black hole therefore see signals that fade and stretch in time. In this sense, the environment near a black hole provides a natural laboratory for exploring how time behaves under extreme conditions. Observations of stars orbiting the supermassive black hole at the centre of the Milky Way have already revealed subtle relativistic effects. Instruments operated by observatories such as the European Southern Observatory track these stars with extraordinary precision. Their motions confirm predictions from Einstein's theory about how space-time curvature alters both trajectories and the passage of time. These measurements demonstrate that general relativity is not merely a theoretical framework, it describes real physical behaviour occurring throughout the cosmos. In environments where gravity becomes extreme, the nature of time reveals its true flexibility. Seconds can stretch. clocks can disagree dramatically. Observers can experience entirely different timelines, depending on their paths through space-time. The calm and steady ticking of time experienced in everyday life therefore represents only one small corner of a much richer cosmic picture. Across the universe, time flows in ways that depend on gravity, motion, and the geometry of space-time itself. And in the shadow of a black hole, time can behave in ways that would seem almost unimaginable from the quiet perspective of a planet like Earth. For more than a century, physicists have worked with two remarkably successful descriptions of the universe. One governs the enormous structures of space, gravity, and cosmic expansion. The other describes the tiny and unpredictable world of atoms and particles. Each theory works beautifully within its own domain. Yet when scientists try to combine them, something strange happens. The two frameworks refuse to fit together smoothly. General relativity, developed by Albert Einstein, describes gravity as the curvature of space-time produced by mass and energy. It works extraordinarily well for planets, stars, galaxies, and the large-scale structure of the universe. Quantum mechanics, on the other hand, governs the behavior of particles and fields at extremely small scales. It explains the structure of atoms, the behavior of electrons, and the interactions of fundamental particles with astonishing precision. Both theories have been tested repeatedly and confirmed by countless experiments. Yet they describe reality in very different ways. General relativity treats space-time as a smooth geometric structure that bends and stretches under the influence of gravity. Quantum mechanics describes the universe in terms of probabilities, discrete interactions, and fluctuating fields. When physicists attempt to apply both theories simultaneously, especially in extreme environments such as the center of black holes or the earliest moments of the universe, mathematical difficulties appear. The equations produce infinities that cannot be resolved using standard techniques. This conflict suggests that a deeper theory may exist beneath both frameworks. Physicists often refer to this hypothetical framework as quantum gravity. A theory of quantum gravity would explain how gravity behaves at the smallest scales and how space-time itself interacts with quantum processes. It would unify the geometry of relativity with the probabilistic structure of quantum mechanics. Finding such a theory has become one of the central challenges in modern physics. Several approaches have been developed in pursuit of this goal. One of the most prominent is loop quantum gravity, a research program developed by physicists including Carlo Rovelli and Lee Smolin. Loop quantum gravity begins with the insight that space-time itself may possess a discrete structure at extremely small scales. Rather than forming a perfectly smooth continuum, space-time might be composed of tiny building blocks. In loop quantum gravity, these building blocks appear as networks known as spin networks. Each link in the network carries a quantum property related to the geometry of space. The connections between these links determine how areas and volumes are constructed at the smaller scales. According to this framework, space is not infinitely divisible. Instead, there exists a smallest possible unit of area and volume determined by the quantum structure of space-time. When these spin networks evolve over time, they form structures called spin foams, which describe how quantum geometry changes from one moment to the next. Within this picture, space-time resembles a constantly evolving web of quantum relationships, rather than a smooth stage on which events unfold. Loop quantum gravity therefore suggests that time itself may emerge from deeper quantum processes. Another major approach to quantum gravity arises from string theory. String theory proposes that the fundamental ingredients of reality are not point-like particles, but extremely tiny vibrating strings. Each vibration pattern of these strings corresponds to a different type of particle. Electrons, quarks, and other particles would simply represent different vibrational states of these underlying strings. One of the striking features of string theory is that it naturally incorporates gravity. Among the vibration patterns predicted by the theory is a particle known as the graviton. which would carry the gravitational interaction. Because of this property, string theory offers a possible pathway toward unifying gravity with the other fundamental forces. String theory also suggests that spacetime may contain additional spatial dimensions beyond the familiar three. These extra dimensions could be tightly curled at extremely small scales, making them invisible to everyday observation. Researchers such as Juan Maldertena have explored profound consequences of these ideas. Maldertena developed a remarkable concept known as the antide sitter and conformal field theory correspondence, often abbreviated as the ADS and CFT correspondence. This idea proposes that a gravitational theory within a certain spacetime can be mathematically equivalent to a quantum field theory, defined on the boundaries surrounding that spacetime. Although highly abstract, the correspondence has provided powerful insights into the relationship between gravity, quantum theory, and information. Closely related to these developments is the holographic principle. The holographic principle emerged from studies of black hole thermodynamics, particularly through the work of physicists Jacob Bekenstein and Stephen Hawking. Their research revealed that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This surprising relationship suggested that the information describing a region of space might be encoded on its boundary surface. In other words, the entire contents of a three-dimensional region could be represented by information stored on a two-dimensional boundary. The universe might therefore behave somewhat like a hologram, where a lower dimensional description encodes the information needed to reconstruct a higher dimensional reality. The holographic principle has become an important idea in attempts to understand quantum gravity. It hints that space-time itself may emerge from deeper informational relationships. This possibility becomes even more intriguing when considering the role of quantum entanglement. In recent years, several physicists have proposed that space-time geometry may arise from networks of entangled quantum states. Entanglement creates correlations between particles that persist regardless of distance, linking their properties in ways that classical physics cannot easily explain. Some theoretical models suggest that the connections formed by entanglement might correspond to the geometric connections that define space-time. In these proposals, the structure of space-time emerges from patterns of quantum information. If entanglement between two regions increases, the effective distance between those regions in space-time may decrease. Conversely, if entanglement weakens, the regions may appear farther apart. This perspective transforms space-time from a fundamental ingredient of reality into something that arises from deeper quantum relationships. Time itself might also emerge from these relationships. Rather than existing as an independent dimension, time could reflect the ordering of changes within the network of quantum interactions that underlie the universe. Although these ideas remain highly theoretical, they illustrate how profoundly the search for quantum gravity could reshape our understanding of time. The steady ticking experienced in everyday life might ultimately be a large-scale approximation of far more subtle processes occurring deep within the quantum structure of reality. Physicists continue exploring these possibilities through mathematical models, theoretical insights, and experiments probing the boundaries of known physics. Whether through loop quantum gravity, string theory, holographic principles, or entirely new frameworks yet to be discovered, the search continues. Somewhere within that search may lie the key to understanding how time itself truly works. For most of scientific history, time was treated as something fundamental. It was assumed to exist as a basic ingredient of the universe, much like space, matter, or energy. Clocks ticked, events unfolded, and the universe progressed through a steady sequence of moments. Yet as physics has advanced, that assumption has gradually begun to soften. Many modern theories now entertain a possibility that once sounded almost unthinkable. Time itself might not be fundamental at all. Instead, time could emerge from deeper processes occurring within the underlying structure of reality. This idea may sound abstract at first, but it follows naturally from several discoveries already discussed. Relativity revealed that time is not absolute. The rate at which time passes depends on motion and gravity. Quantum mechanics treats time differently from spatial variables, raising questions about whether it belongs inside the theory or sits outside as a parameter. Meanwhile, attempts to develop a theory of quantum gravity suggest that space-time itself may arise from more basic quantum relationships. Together, these ideas invite a new question. If space-time can emerge from deeper physics, could time also be something that arises rather than something that exists independently? One of the physicists who has explored this possibility most extensively is Carlo Rovelli. Rovelli's work in loop quantum gravity has led him to consider a relational view of time. In a relational framework, physical quantities are not defined by reference to an absolute background. Instead, they are defined by relationships between systems. Temperature, for example, describes how energy is distributed among particles. Position describes the relationship between objects in space. In the same way, Rovelli suggests that time might describe relationships between changes occurring in physical systems. In this view, the universe does not evolve according to a universal external clock. Instead, change occurs as interactions among physical systems, and time emerges from the relationships among those changes. A simple way to picture this idea is to imagine a universe containing only a few objects interacting with one another. If one object changes relative to another, that change provides a reference for describing evolution. Time becomes a measure of change relative to other changes. Within this relational perspective, time does not exist independently of physical processes. Rather, time arises from them. Rovelli has explored these ideas further through what is known as the thermal time hypothesis. This concept was developed in collaboration with the mathematician Alain Connes. The thermal time hypothesis begins with the observation that thermodynamics and statistical physics already provide a powerful description of how systems evolve. In thermodynamics, the direction of time is closely tied to the growth of entropy. Systems naturally evolve towards states with larger numbers of possible microscopic configurations. Connes and Rovelli proposed that the flow of time experienced by observers might emerge from the statistical state of the universe itself. According to the thermal time hypothesis, the state of a physical system determines the effective flow of time that observers perceive within that system. Rather than time existing independently, it emerges from the thermodynamic properties of the system being studied. In other words, time may arise from the distribution of energy and information across physical states. This proposal has intriguing implications. It suggests that different observers embedded within different physical systems might experience time in ways determined by the properties of those systems. Although these ideas remain highly theoretical, they highlight how deeply the concept of time may be connected to the structure of physical states. Another line of research explores the possibility that time emerges from quantum correlations. In quantum mechanics, systems can become entangled, meaning their properties remain linked even when separated by large distances. Entanglement represents a deep form of correlation between quantum states. Some researchers have proposed that spacetime geometry itself may arise from networks of such correlations. If spacetime geometry emerges from entanglement, then temporal ordering may also arise from patterns of correlation within quantum systems. One way to think about this is to imagine a complex network of interacting quantum states. Each interaction influences others, creating chains of cause and effect. As these correlations propagate through the network, sequences of relationships emerge. Those sequences may give rise to what observers interpret as temporal order. In this sense, time might represent the structure of correlations evolving through the universe. The apparent flow of time would then emerge from how information spreads and interacts within that network. Several research programs explore variations of this idea, particularly in studies of quantum gravity and quantum information theory. The notion that space-time and time itself could emerge from quantum information has become an active area of investigation. Although the mathematics involved is highly sophisticated, the underlying intuition remains surprisingly simple. Time might not be a fundamental stage on which events unfold. Instead, it could arise from the relationships among events themselves. This perspective also connects back to everyday experience in an interesting way. Human beings perceive time primarily through change. Clocks measure motion of gears or vibrations of atoms. Calendars track the motion of Earth around the sun. Biological rhythms track cycles of light, temperature, and activity. Even personal memory reflects sequences of changes stored in neural networks. Without change, the concept of time would lose much of its meaning. A perfectly static universe containing no variation would offer no events to distinguish one moment from another. From this viewpoint, time appears less like a background dimension and more like a description of how change unfolds. If the universe is fundamentally a network of interactions, then time may simply be the language used to describe the order in which those interactions occur. This idea does not mean that time is an illusion in the sense of being unreal. Rather, it may be an emergent phenomenon. Emergent properties appear when many simpler components interact to produce behavior that cannot be understood by examining those components individually. Temperature emerges from the motion of molecules. Waves emerge from the collective motion of water particles. Time may emerge in a similar way from the interactions underlying the universe. If this perspective proves correct, then the flowing timeline experienced in everyday life represents a large-scale manifestation of deeper physical relationships. At the most fundamental level, the universe may consist not of objects moving through time, but of interactions giving rise to the very concept of time itself. For something that may or may not exist in a fundamental sense, time plays a remarkably practical role in everyday life. Human societies depend on timekeeping in ways that are so deeply embedded that it's easy to forget how complex the system actually is. Clocks coordinate transportation networks, synchronize communication systems, guide spacecraft across the solar system, and ensure that financial transactions occur in the correct order. The global infrastructure of modern civilization quietly relies on the ability to measure time with extraordinary precision. For centuries, timekeeping relied on astronomical cycles. Early calendars tracked the motion of the sun, moon, and stars. Mechanical clocks later improved precision through carefully engineered gears and oscillating pendulums. Yet the demand for greater accuracy steadily increased. Scientific research, satellite navigation, and global communication networks require time measurements so precise that even tiny errors can accumulate quickly. This demand led to the development of atomic clocks. Atomic clocks measure time using the natural oscillations of atoms. Instead of relying on mechanical motion, these clocks track the frequency at which electrons within atoms transition between specific energy states. Because these transitions occur with extremely stable frequencies, they provide a remarkably reliable reference for measuring time. One of the key figures in developing these techniques was the American physicist Norman Ramsey. Ramsey introduced methods using separated oscillatory fields that allowed scientists to measure atomic transitions with exceptional precision. His work laid the foundation for the modern generation of atomic clocks used in laboratories and observatories around the world. The atoms most commonly used in these clocks are cesium atoms. Cesium atoms possess a specific transition between two energy states that occurs with extraordinary regularity. This transition defines the modern international standard for the second. The official definition describes 1 second as the duration of 9,192,631,770 oscillations associated with that atomic transition. Although that number may sound intimidating, it reflects the remarkable stability of atomic processes. These oscillations occur with such consistency that atomic clocks can measure time with errors smaller than a second over millions of years. Such extraordinary precision is not merely a scientific curiosity. Modern technologies depend on it. Global navigation systems rely on satellites carrying atomic clocks orbiting Earth. These satellites transmit time signals that allow receivers on the ground to calculate their position. by measuring how long it takes for signals to travel from multiple satellites. Even extremely small timing errors can translate into large positional errors. Because signals travel at the speed of light, an error of only a few billionths of a second could shift a calculated position by several meters. For this reason, satellite navigation systems must maintain extremely accurate synchronization. Relativity plays an important role in this process. Satellites orbiting Earth move at high speeds and experience weaker gravitational fields than clocks on the ground. According to Einstein's theories of special relativity and general relativity, both motion and gravity affect the rate at which time passes. The onboard atomic clocks therefore tick at slightly different rates than clocks on Earth. Engineers must account for these relativistic effects when calibrating satellite systems. Without those corrections, navigation errors would accumulate rapidly. In other words, the strange physics of relativity quietly helps guide airplanes, ships, and smartphones every day. Maintaining global time standards requires careful coordination between scientific institutions around the world. One of the central organizations responsible for this effort is the Bureau International des Poids et Mesures, located in France. This organization works with national laboratories to maintain international atomic time, a coordinated timescale derived from networks of atomic clocks distributed across multiple countries. These clocks continuously compare their measurements, averaging results to create a stable and reliable global reference. Another closely related system is Coordinated Universal Time, often referred to as UTC. Coordinated Universal Time provides the official time standard used for civil timekeeping around the world. Because Earth's rotation is not perfectly uniform, occasional adjustments known as leap seconds are introduced to keep atomic time aligned with astronomical time. These adjustments ensure that civil time remains synchronized with the planet's rotation relative to the Sun. Although such corrections may sound minor, they illustrate how complex the task of timekeeping has become. Maintaining a shared global timeline requires coordination among scientists, engineers, observatories, and international organizations. All of this effort exists simply to ensure that clocks around the world agree on the current moment. Yet behind this carefully maintained system lies the deeper scientific story explored throughout modern physics. The time measured by atomic clocks reflects physical processes occurring at the quantum level. Those processes unfold within a spacetime structure shaped by gravity and motion. Relativity, thermodynamics, quantum mechanics, and cosmology all contribute pieces to the puzzle of what time truly represents. Despite this complexity, the result remains beautifully practical. A precise measurement of time allows aircraft to navigate across oceans, enables financial networks to process transactions, synchronizes communication systems, and supports scientific experiments exploring the nature of the universe. Timekeeping therefore connects the abstract world of theoretical physics with the practical demands of everyday life. Even if the ultimate nature of time remains uncertain, the ability to measure it with remarkable precision has become one of the most important achievements of modern science. Every tick of an atomic clock represents not only a measurement of duration, but also a quiet reminder that the universe operates according to principles far deeper than human intuition once imagined. After exploring the many ways physics, cosmology, and neuroscience describe time, a quiet question begins to linger beneath everything. The clocks tick, the universe expands, stars are born and fade, and memories accumulate in the mind. But what if the flowing timeline that seems so obvious is not a fundamental feature of the universe at all? What if time, as it is experienced, is something that emerges from deeper structures rather than something built directly into reality itself? This possibility may sound surprising, yet several scientific ideas discussed earlier point gently in that direction. Relativity reveal that time does not pass identically for every observer. Motion and gravity alter the rate at which clocks tick, and the concept of a universal present moment dissolves once space-time is considered carefully. Quantum theory introduces further uncertainty. In many formulations of quantum mechanics, time enters the equations as an external parameter rather than as a dynamic quantity within the theory. When physicists attempt to merge quantum theory with gravity, the role of time becomes even more mysterious. Some mathematical descriptions of quantum gravity do not contain a clear variable representing time at all. Cosmology adds another piece to the puzzle. The arrow of time appears closely connected to entropy and the initial conditions of the universe. The direction from past to future emerges statistically from the way energy and matter were distributed near the beginning of cosmic history. In that sense, the flow of time may depend on the specific structure of the universe rather than on an absolute feature of nature. Neuroscience offers yet another perspective. The sensation that time flows smoothly may arise from the brain's methods of integrating sensory information. Neural circuits gather signals across brief intervals and assemble them into a continuous experience. Memory records earlier states of the world, while perception and prediction create a moving narrative that feels like a present moment advancing forward. Taken together, these insights suggest that time may behave differently at different levels of description. At the level of human experience, time flows unmistakably. At the level of physical laws, the picture becomes more complicated. Some physicists have taken these observations seriously enough to propose that time might not exist fundamentally. Julian Barber, for example, has argued that the universe may consist of a vast collection of possible configurations rather than a sequence of events unfolding in time. In this view, each configuration represents a complete arrangement of matter in the universe. What people experience as time passing is the perception of relationships between these configurations. Certain configurations contain records of others, such as memories, fossils, or astronomical signals. These records create the impression that one state follows another, yet within the underlying description, all configurations simply exist within a timeless landscape. Another researcher exploring related ideas is Fotini Markopoulou. Her work investigates the possibility that space-time itself may emerge from deeper quantum structures where time does not initially appear as a fundamental ingredient. In some theoretical models, the universe begins as a network of quantum relationships or information exchanges. Only at larger scales does the familiar structure of space-time emerge. Within this framework, time may arise from the ordering of interactions rather than existing independently from them. These ideas remain highly speculative, yet they illustrate how modern physics increasingly explores the possibility that time could be an emergent property. Long before modern physics raised such questions, philosophers had already reflected on the nature of time from different perspectives. One of the most thoughtful voices in this discussion was the French philosopher Henri Bergson. Bergson distinguished between two concepts of time. The first is the time measured by clocks and described by physics. This kind of time divides the world into precise intervals and treats moments as points arranged along a timeline. The second concept is lived time, the experience of duration unfolding within consciousness. Bergson argued that lived time cannot be fully captured by mathematical measurement. Human experience blends memories, emotions, and perceptions into a continuous flow that cannot be neatly separated into identical units. For Bergson, the richness of lived duration differs fundamentally from the abstract time used in physics. Although Bergson's philosophical views do not provide physical theories, they highlight an important distinction. The time measured by instruments and the time experienced by human beings may represent different aspects of reality. Modern science now finds itself navigating a similar distinction. Physical theories describe space-time structures, entropy, and quantum interactions. Meanwhile, neuroscience studies how the brain constructs a sense of continuity and flow. Somewhere between these perspectives lies the mystery of time itself. Is time a fundamental dimension of the universe, woven into the geometry of space-time? Or does it arise from deeper processes involving energy, information, and the organization of physical systems? For now, science has not reached a final answer. Theories continue evolving, experiments probe ever smaller scales, and observations of the cosmos reveal new clues about the universe's history. What once seemed like the simplest feature of reality now appears as one of its deepest puzzles. Time may be a fundamental thread running through the universe, or it may be a remarkable illusion emerging from deeper patterns of change. Either way, the quiet ticking of every clock reflects a question that scientists are still trying to understand. The exploration of time has taken a long and winding path through many fields of human thought. What once appeared to be a simple background against which events unfold has gradually revealed itself as something far more complex. Philosophers have debated its nature for centuries. Physicists have measured it with extraordinary precision. Cosmologists have traced its connection to the birth and evolution of the universe. Neuroscientists have begun examining how the human brain constructs the experience of time flowing from moment to moment. Each discipline approaches the question from a different angle, yet all arrive at the same quiet realization. Time is not nearly as straightforward as everyday experience suggests. For Isaac Newton, time was absolute. In his view, time flowed uniformly throughout the universe, unaffected by the presence of matter or motion. Every clock, no matter where it was located, ultimately measured the same universal ticking. This picture proved remarkably successful for describing the motion of planets and falling objects. For centuries, it provided the foundation for scientific understanding. Then, in the early 20th century, Albert Einstein introduced a radically different idea. Through the theories of special relativity and general relativity, Einstein showed that time is woven together with space into a unified structure known as spacetime. The rate at which time passes depends on motion and gravity. Clocks carried aboard fast-moving spacecraft tick differently from clocks resting on the surface of Earth. Clocks placed in stronger gravitational fields tick more slowly than those farther away. In this new view, time is no longer a universal river flowing at the same pace everywhere. Instead, it bends and stretches in response to the structure of the universe itself. Another profound insight came from the work of Ludwig Boltzmann, who connected the direction of time to the statistical behavior of matter. The increase of entropy described by the second law of thermodynamics provides the arrow pointing from past toward future. The reason memories exist, eggs scramble rather than unscramble, and stars gradually burn through their fuel, is ultimately tied to the way energy spreads through physical systems. This connection between time and entropy suggests that the flow of time may arise from statistical patterns rather than from a fundamental physical law. In more recent years, new ideas have emerged that push the question even further. Julian Barber has argued that time may not exist at the deepest level of reality. According to his proposals, the universe could consist of a vast collection of possible configurations, each representing a complete arrangement of matter. What people interpret as time passing may simply reflect relationships between these configurations. Carlo Rovelli has explored related ideas within quantum gravity, suggesting that time might be relational rather than absolute. In certain theoretical frameworks, time emerges from interactions between physical systems rather than existing as an independent dimension. These proposals remain subjects of ongoing investigation, yet they highlight how deeply modern science is rethinking the concept of time. Meanwhile, cosmology continues revealing a universe whose history stretches across immense spans. From the earliest moments after the Big Bang to the formation of galaxies, stars, and planets, time has shaped the unfolding structure of the cosmos. The light arriving from distant galaxies carries information from billions of years in the past. Observing the night sky therefore becomes a form of looking backward through cosmic history. At the same time, neuroscience reminds us that the experience of time is partly constructed within the mind. Neural processes weave sensory input and memory into a continuous narrative that feels like a present moment moving forward. The brain's perception of duration can stretch or compress depending on attention, emotion, and context. Moments of excitement may seem to pass quickly, while moments of anticipation feel longer. These subtle distortions illustrate that lived time is not identical to the abstract time described by physics. Taken together, these perspectives reveal a remarkable picture. Time connects the smaller scales of quantum theory to the larger structures of cosmology. It links the ticking of atomic clocks to the expansion of the universe. It shapes biological rhythms, human memory, and the long evolution of galaxies. And yet, despite its central role in nearly every aspect of reality, the ultimate nature of time remains uncertain. Perhaps time is a fundamental dimension embedded within spacetime. Perhaps it emerges from deeper relationships between energy, information, and matter, or perhaps the flow of time experienced in daily life reflects the way consciousness organizes events into meaningful sequences. Whatever the final answer may be, the search itself reveals something extraordinary. The simple act of measuring moments has opened a doorway into some of the deepest questions science can ask. Questions about the origin of the universe, the structure of physical law, and the nature of reality itself. In quiet moments, it becomes possible to appreciate how every passing second belongs to a vast cosmic story. The atoms within the body were forged inside ancient stars. The planet beneath one's feet formed billions of years ago. The universe has been unfolding through immense stretches of time long before human awareness appeared. And perhaps, as scientific understanding continues to grow, the investigation of time will lead to an even deeper realization that what seems like the steady ticking of moments may ultimately reveal something profound about the structure of the universe and humanity's place within it.